Okay, we're going to continue talking about acid-base equilibria, focusing on strong acids, strong bases, and moving on to weak acids and weak bases. So first thing you should do is go back and take a look at those 7 strong acids that we talked about at the beginning of the year. I'm not sure why this one is not subscript, but these should look familiar to you. Go back and really learn them. And then I also listed some strong bases. And what you'll notice about the strong bases, when you put them in water, they completely disassociate. And most of these are alkali metal hydroxides. And then a few of them you can see over here are the heavier alkaline earth metal hydroxides. So take another look at these. Be familiar with them. And so basically with strong acids, the thing you really need to know about them is they completely disassociate in water. And so this is hydrochloric acid. And you see when you put hydrochloric acid in water, it completely disassociates. So really what you have is something like this. You have hydrochloric acid, an arrow going in one direction, forming H plus ions. Let's try that again. H plus ions and chloride ions. Now, being a strong acid, these H plus ions will then find water and form hydronium ions. So one of the things you probably should know is we'll use H plus and hydronium interchangeably. They really mean the same thing. And you can see when you take a look in this solution, you can see the hydronium there. That's really, those are the H pluses as well. And then you see your Cl minuses there. So that's basically what strong acids do. They have an arrow going in one direction and they completely disassociate. So let me get rid of that because I just wrote over top of it. So for monoprotic acids, which all of the acids above are monoprotic except for sulfuric acid, and we'll talk about that, the concentration of hydronium is equal to the concentration of the acid. So in other words, if I have a 1 molar solution of hydrochloric acid, I would expect to have 1 molar Cl minus ions in solution and 1 molar H plus or hydronium ions in solution. So here's a typical question. An aqueous solution of nitric acid has a pH of 2.34. What is the concentration of the acid? So taking a look, let's go ahead and let's just write out what this looks like when it disassociates. Being that nitric acid is a strong acid, it is going to completely disassociate into H plus ions and nitrate ions. And so the concentration of my acid also becomes the concentration of both of my ions because it's a 1-to-1-to-1 ratio. So the question is, what is the concentration of the acid? Well, what I really need to figure out is what the concentration of H plus is, because then I will know the concentration of my acid since they are the same. So the concentration, oops, pretend like you don't see that. The concentration of H plus, then we can go in and we can kind of take a look. I'm going to take a look at this equation right here. Since I know the pH is 2.34, let me go ahead and write that down. pH equals 2.34, and that is equal to the negative log of the concentration of H plus. Go. Then I can go ahead and solve for this. And so plugging this in, I get the concentration of H plus is equal to 10 to the negative 2.34. And when you plug that into your calculator, you end up getting, I love this answer right here, 0.0046 molar. All right. Next, let's take a look at strong bases. So strong bases, same thing. If this was sodium hydroxide, we would say that it would 100% disassociate into sodium ions and hydroxide ions. So those are our OH minus ions, and those are our Na plus ions. And so by definition, a strong base is something that completely disassociates. what you have to keep in mind is if you have a strong base that is, for example, like calcium hydroxide, then you're going to get double the concentration of hydroxide ions. And that's going to become important later. We'll take a look at an example problem with that. So if it's an alkali metal that completely disassociates, everything's a 1-to-1 ratio. But if it's an alkaline earth metal that's a strong base, we have a 1-to-2 ratio. So what is the concentration of a solution? For the pH of 11.89, but we're actually looking for the concentration of KOH. So watch out for this, because a lot of times they'll give you the pH and they're going to ask for the concentration of a hydroxide or a strong base. So it really helps if we look at this from the standpoint of really POH. So knowing that, I'm going to write this up here, pH plus POH are equal to 14, and that comes off your equation sheet, I'm going to go ahead and just calculate what POH is here. And the POH of this first problem ends up being 2.11. And the POH of the second problem here ends up being approximately 2.32. Okay. And the reason I did that is because I know my concentration of KOH is going to be equal to the concentration of my OH minus. And so I'm going to go ahead and I'm going to use POH is equal to 2.11, which is equal to the negative log of the concentration of OH minus. And by doing that, I can go ahead and plug this in the same way, and we end up getting the concentration of OH minus equals, let's see, 10 to the negative 2.11. Oops. Which gives us 7.8 times 10 to the negative third. Again, I think when you calculate that out, you get like 0.00776. Since this has 2 decimals in the pH or POH, I'm going to round to 2 significant digits, and that's why I get that answer. Okay, we're going to go ahead and work this one out as well. I'll work that one out over on this side. This one's a little bit different because I have twice the number of hydroxide ions there. So what's going to happen in this case is my calcium hydroxide is actually going to disassociate into Ca2 plus and 2OH minus. And so the concentration of calcium hydroxide is going to be, go back. There we go. Is going to be 1/2 the concentration of OH minus. Or in other words, the concentration of OH minus is twice that of my calcium hydroxide. So keep that in mind. We're going to do the calculation the same way. We do the concentration of OH minus is equal to 10 to the negative 2.32. When we do that, we end up with, oh boy, this is so touchy today. We end up with, let's see, I think I got 0.004786 molar. And then I'm going to divide that by 2 because I have twice the concentration of hydroxide as I do for my calcium hydroxide. And they're asking you for the concentration of calcium hydroxide. So that is how we come up with this answer. All right. I'm going to go ahead and stop there and just stop this for strong acids. I'm going to do a second video for weak acids.